Okay, so today we will first look another parameterization of curves. So this is the polar parameterization. However, you've seen this already at lab sessions, so we will go through this polar parameterization a little bit quicker. And then after that, we will do parameterization of surfaces. And if time allows, we will start with differential equations already today. And we will be dealing with differential equations and systems of differential equations till the end of this course. So another possibility to parameterize a curve is by using polar coordinates. You know from calculus that polar system, in the polar system, we need polar radius r and polar angle of the point. And then we can simply say for each angle, we only need to know the radius. And if we, for each angle, if you know the radius, then we will know where the point on the from the curve lies. So we have r to be the, so r is a function of the angle, and it can be, angles can be from not only from 0 to 2 pi, but from 0 to infinity. And usually this radius is positive. We could do an arrangement that if radius is negative, then it means that we have to then we have to put it on the other side of the origin. But usually it will be positive for us. So it will be a mapping from 0 to infinity into 0 to infinity. And for each, so it's a function of the angle. So for each angle, we get some positive real number. So for example, at angle 0, we have r0. So let's say that at angle 0, we have r0. And then we increase the radius to, for example, pi over 6. And on this line, pi over 6, we have to know what's the polar radius. And let's say that this is polar radius, r of pi over 6. And then we increase the angle. We have, for example, pi over 2 pi over 6, so it's pi over 3. Again, we have to know what's the radius. Let's say that it's r over pi over 3. And also, for example, pi over 2, and so on. And then we just connect all those points. And so on. And you see, pi can be bigger than 2 pi because the angle could be bigger than 2 pi because when we come back to, so when we do 2 pi, then we come back to x-axis again, but it doesn't mean that we have to be again in the point r0. So we can be in another point. So for example, r over r of 2 pi, and so on. And we can continue this traveling. Also in this way, we get one-dimensional object, which is a curve. So if we are given the equation of the curve in the polar coordinates, it's very easy to get the expression in the usual Cartesian coordinates by those equations, and also vice versa. If you have a curve in Cartesian coordinates, then we can get easily the expression for the curve in polar coordinates. So you all know from analysis or even from the high school that x is r times cosine of phi, and y is r times sine of phi. And on the other hand, r is just square root of x squared plus y squared, while this phi, this is that just arcus tangens of y over x. So we have to be a little bit careful here. So this is arcus tangens of y over x if we are in the first quadrant or in the fourth quadrant. Otherwise, we have to also add pi if we are in the second or third quadrant. Now we will see a few examples of the curves in polar form. So defining a circle in the polar coordinates is very easy. The unit circle is just r equals to 1. So for every angle, the radius must be 1. And we get the unit circle. For example, if r is equal to phi, so then when phi is 0, then r is also 0. Then phi starts to grow, and also r grows with the same size. For example, we can draw a few points. So phi is pi over 3, or phi is pi over 2, then r must be also pi over 2. This is 1, then pi over 2 will be somewhere here. And then phi will grow slowly, and r will grow with the same size. When phi will be pi, then r must be also pi. 1, 2, 3. So pi will be here, somewhere here. So this will grow like that. And when phi will be pi over 3 pi over 2, also phi will be 3 pi over 2. And so on. And if you draw this with some program, for example, MATLAB, then you see that what we get is a spiral, and it's called Archimedean spiral. Then here is one example how to parameterize line in the polar form. So here we have r is 1 over sine phi. How would we see that we get exactly the line y is equal to 1? So we have x is here by the expression above. So recall here that x is r times cosine phi. So x is r times cosine phi. So it's just cosine phi over sine phi. And as this is cotangent of phi. And as phi runs over all possibilities, cotangent runs over all real numbers. So x goes over all real numbers, while y is r times sine phi. So it's 1 over sine phi times sine phi. And this sine phi and sine phi factor out. So what we get is 1. So y is constantly equal to 1, while this x, the codomain of x is all real numbers. This means that we really live on a line, which is y equals to 1, and x goes over all real numbers. And there is also one interesting curve, which is called cardioid, because it somehow describes the heart. And it's given by the polar form 1 minus sine phi. You can try to sketch this curve by yourself, but it's called cardioid because it looks like a heart. For example, you can try to draw different curves using Mathematica. Here, I will show you one example. So we have here the curve in the polar form. So A is my angle. So it's sine of A minus pi over 12 to the power of 5 plus e to the power of sine A minus 2 times cosine 4A. And we will see what's this curve. And it has a special meaning. We will see shortly. So for example, first I will just draw it for A from 0 to 2 pi. And this is this picture. So we start in -1, and then we travel. And as the angle gets pi over 2, you get r, which is approximately 0.7. Now I will draw the same curve, only that I increase the angle. So now the angle will go from 0 to pi. So you see, I continue traveling, and this you could notice that this expression for the curve is so the curve is even. So it's just so this part from pi over 2 to pi is obtained just by reflecting the part of the curve from 0 to pi over 2 over the y-axis. Probably you don't see, you cannot guess what would be the name of this curve from those two pictures. So let's increase the radius for another pi to 0 to 2 pi. And now we already see a better picture. And you could try to guess what's the meaning of, what's the name of this curve. So the name of this curve is butterfly, because you see that it describes butterfly-like shape. And if you increase the angle even more, so from 0 to 2 pi, then this picture gets something like that. So it really resembles butterfly. Okay, and we can also compute lengths of the curves. So if we are given the curve in the polar form, we can easily compute the length. So from last time, you can recall that, so what was the length of the curve? So the length of the curve given in the parametric form was, just let me write this down. So we have integral from the left endpoint to the right endpoint, and we have to integrate 1 over 2. Why this 1 over 2? Because if you remember how we derived this formula, we were integrating areas of triangles. So that's why we have this 1 over 2, because this is 1/2 over of the area of the parallelogram with the sides, which are exactly position vectors at the two consecutive endpoints. And the area of the parallelogram is absolute value of x, y prime minus x prime y. This is what we did last time. So this is from last time. Length of the arc from A to B of the curve given by f of t is equal to xt yt. And now we can plug in for x, we can plug in polar form. So it's r times cosine of phi. And this y is r times sine of phi. And then y prime is then minus, so it's r times r prime. So we have to, yeah, here we have to be careful. So r times sine phi. If we try to take the derivative with respect to the parameter t, so now r is a function of t because it depends on t. And the same holds for this sine of phi, because phi is a function of t. Both r and phi are functions of t. So when we take the derivative with respect to t, we have to use the product rule. So we differentiate r with respect to t and multiply by the other function, and then plus we differentiate sine with respect to t and multiply by the first function. And then if you do this, if you plug this in above, so after some calculation, we get that this star is equal to 1/2 of the integral of r squared of d phi. And this phi goes from alpha to beta. So this alpha and beta, when t is equal to a, phi is equal to alpha, and when t is equal to b, then phi is beta. So you can do this calculation by yourself, but yeah, the most important part in this calculation is that we differentiate in the appropriate way. So in this way, so that we use that r and phi are functions of t when we take the derivative with respect to t. And this is the formula for calculating areas in the polar form. Probably you remember this formula from last year. And to conclude with curves, let's only recall the connection with motion. So parameterization of curves. And motion in R3. So let's RT be the position vector at time in R3 at time t. What is then R prime of t? So R prime of t, this is the velocity vector in R3 at time t. And then the second derivative of the position vector is the acceleration vector. In R3 at time t. And how to obtain, so we have this motion, let's say that this is our position vector. This is the trace of our path. So it's RT. And how to obtain the length of our travel. So distance traveled. So let's say that this is R of 0 and this is R of t. Distance traveled from 0 to from time 0 to time capital T. This is integral from 0 to capital T of the norm of the velocity vector. So this is what we derived last time or before 2 weeks. The arc length of the travel is just the integral of the norm of the derivative of our position vector at a given time with respect to time. Okay, this is all regarding curves. And now we will switch to higher dimensional objects. And these will be two-dimensional ones. Those are surfaces. Before we go to surfaces, there may be any question regarding curves?
Yes, I have one question before for the formula for an area in the polar plane. That formula is for the area bounded by the vectors from the coordinates origin and the points alpha and beta.
Okay, if not, then let's go to surfaces. There was a question, but I didn't hear it. Can you repeat, please?
Yes, can you hear me?
Yeah, now I can hear you, yes.
Okay, for the formula in the section for area bounded by curves in the polar plane.
Yes.
That formula is for the area bounded by the two vectors that go to 2 points from the coordinate axis, right? Not like straight below.
Okay. Yes, this is the formula. Yeah, you mean this one in the orange box?
Oh, yes, that one.
Yeah. This is the formula for, as you said, yes. So we have this, our curve, and this is the formula for this area, for example. If this is alpha and this is beta. So this is angle alpha and this is angle beta. So this is the formula for this part, yeah. To compute the other area, for example, this one, this green one, we would need to express y with respect to x. So to compute this, we would need to know how y is expressed, to know the expression for y with independence to x. So if we don't know this expression, then we cannot easily compute this area. Maybe some other question? I mean, we could do this numerically. So we could compute enough x's and enough y's so that we would get enough points here. Let's say that we would compute enough points on this line. And then we would do numerically. So sum up those trapezoids. Yeah, so if we had x naught, y naught, then x1, y1, then x2, y2, and so on, xn, yn. And then we compute the trapezoid. So this is this point, and this is this point. And we compute this area by this trapezoid rule. So it's A, B, so, and C, and it's C times A plus B over 2. This is how the formulas, the basic formula for numerical integration works. So it's based on exactly on this trapezoid rule. So yeah, if we cannot express y in terms of x, we can do this discretely. So compute enough points and then use trapezoid rule. Okay, let's go to surfaces. So we are going one dimension higher. We add another dimension. So when we were working with curves, we had a vector function from the interval to Rm. So E was an interval. This was a subset of R. So this was a one-dimensional object. And now we add another dimension. So we have D, which is a two-dimensional subset of R2. And again, vector function from D to Rm. So the map of f of D will be two-dimensional. So let's see below. This D can be the easiest example for D is a rectangle. So this is D. We have X and Y, and this D is a rectangle. And for each point in D, we prescribe the value of, so f of, so if this is UV, then we map it. FUV is then the point on our surface. So this point corresponds to the point on our surface. So this is f of u v. And if we do this for each point in our D, the image of this set D is then a surface in R3. So this image, f of D, is called the surface. Why? Because it's two-dimensional. You all know example of surfaces from linear algebra. So the surfaces with constant curvature, we defined curvature for curves. The curvature can be extended to surfaces also, but as you can imagine, what would be the constant curvature? What would be the surface with a constant curvature? So the curve with constant curvature was a line. So the surface with constant curvature would be a plane. So this is not a surface with constant curvature, but so the surface with constant curvature would be a plane, which you all know from linear algebra. So for example, it would be something like that. So an example of a surface. And you also know how to parameterize this surface. So there are two ways. One parametric way is the following. So we have to come up to the surface. We just choose one vector, one point on the surface. Let's say R0. And since this is a two-dimensional object, it is enough to know two vectors, two linearly independent vectors from this surface, from this plane, to describe all other points. So let's say this is first E1, and then the second E2. So we travel with this green vector to the plane. We come to this point R0, and then we move in the direction of E1 for some scalar multiple of E1, and then we move in the direction of ER of E2 for some scalar multiple of E2, and we travel along. We can reach all points on this plane. So every point, for example, this point, this is R0 plus some parameter U times E1 plus some parameter V times E2. And this U and V are real numbers. So this is the parametric expression for the plane. So plane parametrically is just the function f from, let's say, D. In our case, this will be R squared to R3. So it is UV, the pair of parameters UV are mapped into R0 plus U times E1 plus V times E2. So this is plane parametrically. And to conclude this first hour, let's recall how to express plane in the Cartesian coordinates. So this means that it has to be given, since this is a two-dimensional object in R3, it has to be given with one equation. And as you can recall from linear algebra, the equation of the plane is ax plus by plus cz is equal to d, where this a, b, c, and d are real numbers which determine the plane. And in our case, so what is this? What is the meaning of this ABC? This ABC, if we collect this ABC in the vector, it's just the normal to the plane. So it's the normal vector. The normal vector to the plane. So it's this vector up here. And how do we get this normal vector? If you know E1 and E2, then this normal vector is perpendicular to both of them. And this means that it is enough to compute the cross product of E1 and E2 to get this normal vector. So N is obtained by computing the cross product of E1 with E2. And once we know this normal vector, it only remains to determine D. So once we know N, we have to determine D. And this is only by knowing one point on the plane, because there are one-dimensional, there is one-dimensional possibility. So D is a real number. As D varies over all real numbers, this plane moves along along the z-axis, so up and down. So we have to fix the height, and the height is fixed by knowing one point on the plane. So for example, R0. So D is determined by plugging R0, this is X0, Y0, Z0 into this expression star. So we have calculated the normal vector, so ABC, because normal vector is ABC, and then we plug in X0, Y0, Z0, and what we get is then D. So we know how to come from the from the parametrically given plane to the Cartesian plane in the Cartesian coordinates. However, vice versa, how would we get the plane parametrically if you are given Cartesian coordinates? Does somebody remember? So we are given plane parametrically, and we have here the algorithm how to get plane in the Cartesian coordinates. What about vice versa? We are given the plane in the Cartesian coordinates. How would we get plane parametrically? So there are many parametrizations of the plane, but how would we determine one of them? Does anybody see? This was plane parametrically into play in Cartesian plane in Cartesian coordinates. What about vice versa? Plane in Cartesian coordinates. into plane in parametric coordinates. So plane in Cartesian coordinates, this means that we have ax plus by plus cz is equal to d. Let's look at the image again. So how would we determine this green, blue, and orange vector? What do we need to do? Does anybody see? It's not difficult. Just look at the picture. So we have here 1 point, and then E1. Let's say that it ends in another point, A, B, and then so this was E2, and E1 ends in another point. So A, B, C completely determine green, blue, and orange vector. So the question is to determine 3 points to find 3 points in the plane, and from 3 points in the plane we are able to compute all 3 vectors. So all what we need are 3 points on the plane, A, B, C, and then we can choose R0 to be just the position vector of A, and then E1 is the vector from A to C, and E2 is the vector from A to B. So the only thing which we need to do is find 3 points on the plane. And to get A, we can simply take try to compute A00. Let's say here. So X00, the candidate for B is 0Y0, and the candidate for C is 0, 0, Z. These are the most natural candidates, and we plug them here, and we get that X is D over A. If A is non-zero, if A is 0, then this candidate is not appropriate. So we can we must change this A, and then B is D over B. If B is non-zero, again, if B is 0, then we have to then this candidate is not appropriate. And for C, Z is D over C if C is non-zero. Okay, are there any questions? Okay, if not, then let's do a 15-minute break. And we continue at 10:28. So we've seen plane in Cartesian and plane in parametric coordinates. To motivate the second hour, what we will study is are 3 types of coordinates. So first one, we already know, Cartesian coordinates, and then we will study cylindrical coordinates. Why cylindrical? Because those coordinates are the most appropriate to express the cylinder. So in these coordinates, it will be the most appropriate to give the definition of the cylinder. And then there will be one coordinates which are most convenient for expressing spheres, and they are called spherical coordinates. They are natural generalization of polar coordinates. So polar coordinates are the easiest to express the circle. So those spherical coordinates will be natural generalization, and we will only look at the generalization to R3, but they also have generalizations to higher dimensions. So they are the most convenient to express the sphere. And we will use both of them to express torus. So expressing torus. So what is torus? So it's donut. So it's a donut with a hole inside. And this torus is important in robotics because it can describe the motion of a robot which have two levers. So one is this one from here to the center of the torus, and then the second lever is this one. So with this torus, we can describe the motion of a robot with two levers, with two arms. And we will learn how to express the torus, how to easily define all the points on the surface of the torus. And we will also see how to compute tangent planes to every parametrically given surface. So how to compute tangent planes to surfaces. So tangent plane here in case of cylinder, it's just this one. In case of, so this is, for example, in every point. Here in terms of, in case of sphere, we have something like that. And in terms of torus, it's, example, in some point, it's something like that. So we will see how to compute those tangent lines, tangent planes. Okay, let's start with the cylinder. So I will just continue here on the right side. So we need two coordinates. How would you easily give the equation of the cylinder, parametric equation of the cylinder? Let's say that the cylinder has, so the radius is rho, and this is a fixed positive number. And we would like to express every point on the surface of this cylinder. Let's go in the Cartesian coordinate system. Let's say that we have here a cylinder. Okay, so how would you give the equation defining, for example, this point, this violet point? So this point, this is x, y, z. And let's say that the height, we can use two parameters because it is a surface. So we would like to use two parameters. And so the height, let's say that height will be one of the parameters. So one of the parameters will be height. which means that this height, this is one of the parameters, and it's just z. So z is one of the parameters used, and this z can vary. So if we have infinite cylinder, it can vary from -infinity to infinity. So this z is from -infinity to infinity. And now it only remains to, we only have one parameter left, and we have to express x and y. And this is quite easy. So for example, if we know, so we know what's the distance between this point to the z-axis. So this distance is exactly the radius, which is rho. And let's say that we will move this point in the xy plane. So let's say that it comes here. So that is this point where we just put the last coordinate to 0. So here it was x naught, y naught, z. And now we put it in the xy plane. So it's x naught, y naught, and 0. And we only need to know the angle, the polar angle of this point. We know the distance from this point, x naught, y naught, to the origin, because it's just rho. And we only need the angle between this position vector and the origin, so in the x-axis. So I will draw here another picture. So if we are in xy plane, and we have here point x naught, y naught, we know that this distance is exactly the radius of the cylinder, rho. So it remains to know this angle phi. And this is our parameter. So here we have, so then x naught is rho times cosine phi, and y naught is rho times sinus phi. So we have here rho cosine phi and rho sine phi. Rho cosine phi and rho sine phi and z. This rho is fixed, so phi and phi runs over from 0 to 2 pi. And these are cylindrical coordinates. These are called cylindrical coordinates. So rho, phi, and z are cylindrical coordinates. Of a point in R3. So rho, recall that rho is the radius or the distance. In other words, this is the distance from the z-axis then z is the height of the point, and phi is the polar angle in the xy axis. So phi varies from 0 to 2 pi, and z varies from -infinity to infinity. All those points then describe the cylinder. Okay, these were cylindrical coordinates. Let's go to the spherical ones. So now we'll go down. Spherical coordinates, which are the most convenient tool to define the sphere. You see, if you try to describe the sphere with using the cylindrical coordinates, you won't be able to do it because so yeah, if rho. So this is because the distance from z-axis of every point on the sphere changes. So here, when we had the cylinder, every point had constant distance from the z-axis. This was rho. So to express the sphere, the distance of the point to the z-axis should be the same, but it's not for every point, which means that we cannot simply describe the sphere using the cylindrical coordinates. We need another coordinates, more convenient ones. So let's take a sphere. Let's draw a sphere in R3. Okay, so it's something like that. Let's take one point on the surface. So let's take this point. Okay, connect it with the origin. Okay, and as above, as for the cylinder, if we, so this is x naught, y naught, z naught. And let's map this point in the xy plane. So it's x naught, y naught, and 0. Okay, and let's try to express x naught, y naught, and z naught. So for x naught, y naught, we can again use polar coordinates. So if we know this phi, then so if we know phi, then x naught will be rho, but this rho is not constant now. This rho, this is the distance from z-axis. It now depends on the point. So I will write this rho as a function of x naught, y naught, z naught times cosine phi. So in case of the cylinder, this rho was constant. However, now this distance is the function of the specific point on the surface of the sphere. And then y naught is rho, again, x naught, y naught, z naught times sine of phi. So this phi is again one parameter. And we need another one. Again, let's fix the radius of this sphere. So let's say that the radius of the sphere is capital R. So R is the radius. And so also then this length is R. And what we need here, what we need is this orange. This is rho of x naught, y naught, z naught. So we need to somehow express rho with R and some other parameter. And of course, z naught must be also expressed using R and some other parameter. So this should be functions of R and some other parameter. Do you see what would be the convenient parameter with which we could express both rho and z naught? Does anybody see what other parameter should we take?
maybe the angle from z coordinate
to z coordinate with angle with, so the angle of this position vector, and the angle with what?
Z coordinate.
So z coordinate, so this is the position vector, but we had to measure the angle. I know which angle you mean this angle, but what is this angle? So this is the angle between the position vector and of the point and the xy plane. So yeah, this is the most convenient parameter. This is this angle psi. It's the psi. This is the angle between the position vector of the point. So between x naught, y naught, z naught, and xy axis, xy plane. And you can see that this angle varies from minus pi over 2 to pi over 2. So this angle only goes from minus pi over 2 to pi over 2. And taking this angle, then z naught is r times sine of this angle, while rho is r times cosine of this angle. And this is our second parameter. So these are the most convenient coordinates called spherical coordinates, in which it's the most convenient to give the equation of the sphere. So let's write them again. Spherical coordinates. X is r times cosine of psi times cosine of phi. And then y is r times cosine of psi times sine of phi. And z is r times sine of psi. And this psi only goes from minus pi over 2 to pi over 2, while phi goes from 0 to 2 pi. And if you try to express the cylinder in those spherical coordinates, you again won't be successful. So expressing sphere in the cylindrical coordinates isn't possible, and in a simple way, and also the other direction. So expressing a cylinder in spherical coordinates is not simple. So these are the second coordinates. And I mentioned that we can do this also for higher dimensions. So if we describe the sphere in R3, if we had a sphere in R4, then it turns out that we need another angle. So phi, psi, and then let's say psi, and also psi will go from minus pi over 2 to pi over 2. So for each dimension we add, we need another angle which goes from minus pi over 2 to pi over 2. But it's impossible to draw this. So once we do this parameterization, it's possible to compute that the length of every point is really 1. So it really lives on the sphere in higher dimension, but it's impossible to draw a picture beyond 3 dimensions. Okay, and finally, we will be able to also give the equation of the torus. So equation of the torus. It's the most convenient way to give the equation of the torus is to look at the torus as the surface of revolution. I will shortly tell you what this means. So we have three-dimensional. So we have R3, X, Y, and Z. And I will draw a torus here in XZ. So I will draw just the intersection of the torus with XZ plane. So we have XZ plane. So the intersection of the torus with XZ plane will be a circle. So on one side and also on the other. So here. And then we rotate this circle around around Z axis. So we rotate the circle around Z axis, and what we get are circles. So here and here. Now I'm rotating. So what I'm drawing is a trace of this point. So I took this point and I'm drawing its trace when we rotate it around Z axis, and we get a circle. And then I will do the same for this point. For the yellow point, again, I will rotate it around the Z axis, and I get a bigger circle. But if I fix, so if I intersect this with some plane which is in which Z axis lies, I get a circle. For example, if I get the circle here, and then I get the circle here, get the circle here, and so on. I get the intersections with the planes are circles. So, but recall that the picture of the torus is this. So this is a donut with a hole. Okay, and why I did this in this way. So let's again focus on this circle in the XZ plane. And let's first parameterize this circle. So we need, let's say that the center of this circle is on the distance small a from the origin. So this point is in fact a not a0, 0. And then we need the radius of this smaller circle. So the radius, let's say that the radius is b. So what is the parameterization of the points on this circle? So this point has parameter, so a plus b times, and here I have angle, let's say psi, cosine psi, and then I have sine psi, so so this is y is 0, y is 0, and z is b times sine psi. And this psi goes from 0 to infinity, from 0 to 2 pi, and then it starts, the points start to repeat. So it's enough to take psi from the interval 0 to 2 pi. And then what we do with this circle, so this is the parameterization of the circle, of the violet circle. And then what we do is only rotate it around the z-axis. So when we will rotate this circle around z-axis, we will need another angle, which will measure the for what angle we rotate. Here, this angle was 0, but then, for example, at this first black circle, the angle was something. Oh, sorry. So at this first circle, the angle was some psi. No, we already used psi, let's say phi. And then it was phi 2, and then it was phi 3, and so on. So we rotated this circle around z-axis, and what was in fact the equation of all those circles. So we had a plus b times cosine of phi. This is x-axis, and I will leave some room, and here I will write a plus b cosine phi, and I will leave here some room. And then the last coordinate, when we rotate this circle around z-axis, z is constant. For every point when we rotate around z-axis, z is constant. So here I have d times sine psi. So the rotation around z-axis doesn't impact on the last coordinate. However, what we have to fill in here in the unknown spaces. So here we have cosine of phi here we had psi, and here we had psi, sorry. So psi. So here we have cosine of phi, because this determines, so we rotated for phi, and cosine of phi of this rotation of this part goes to x-axis, and then we rotated for phi, and what's the impact on the y-axis? It's exactly sine phi. So you can think of this, why I put exactly cosine phi and sine phi here. You can think of this like we were in the xy plane. I have here some point r, so let's say r naught, and then I rotate this around the origin. What's the And here I have a point, for example, x1, y1, with respect to this angle phi. So what are the coordinates of this x1, y1? The coordinates of x1 are r times cosine phi, and x2 is r times sine, y1 is r times sine phi. Okay, this is clear. And here, in the expression above, this was our r. Because we had a point in the x, z plane was this a plus b cosine phi, 0 b sine phi. So the point in the xy plane was a plus b cosine phi 0. So this a plus b cosine psi was r. And then we rotated this point r0 around z-axis. So that's why we had here r times cosine phi and r times sine phi. And here phi runs from 0 to 2 pi. And psi also ran from 0 to 2 pi. And this is the parameterization of the torus. So f of phi and psi is equal to a plus b cosine psi times cosine phi, and then a plus b cosine psi times sine phi, and b sine psi. So here a is so the length of one lever, and b is the length of the second lever. So this is A, and this is B. And this is here is the connection with robotics. So we have a robotic arm, which has two levers. So one is this. This can move around, this can rotate around Z axis. And then the other lever can rotate around around this point, around this center in the plane. So this is of length B. And so what is the surface that the arm can reach? It's exactly torus. And this is the parameterization. So was this derivation clear? Or are there any questions? Okay, then let's conclude. Let's do another 15 minutes to conclude this chapter on surfaces. And then we'll do a break. And after break, we start with differential equations. Okay, so we saw spherical coordinates, cylindrical coordinates, and now we also saw how to express a torus. And we express the torus as a surface of revolution. So it can be, this idea can be generalized. So surface of revolution. What does this refer to? Let's say that we have some curve in the xz plane. So let's say that, or yz, let's say yz plane. So we have x, y, and z. And here we have some curve in the x, this is in this plane, xy plane. And this is the equation of the curve. I mean, the graph of the curve. This curve is given by r of t is equal to xx, so x coordinate is 0, and then y coordinate is something, y of t, and then z coordinate is something, z of t. And now we rotate, that's why this is the surface of revolution. So we rotate this curve around z-axis as we did with the torus. And what we get, so we rotate around z-axis every point. Every single point describes some circle. And what we get is some surface of revolution. Of course, my picture is very bad, but I hope you got the idea. So I rotate every point, and what I get is then symmetric body as a surface. So the surface of this body is obtained by rotating the initial curve around z-axis. And I can easily describe the equation of this surface. So this is this surface. So the definition, the parameterization of this of the surface by the same idea as above for the circle and for the torus, we have RTU. So z-axis is independent of this rotation. This u will measure the angle of rotation. So this third coordinate is independent of this u. It remains z of t. While on the first coordinate, we saw that first coordinate becomes y of t times cosine of u. And the second coordinate becomes y of t times sine of u. And the third coordinate, as I said, remains constant. So t runs from the initial interval. Let's say that this was interval I, while u is now the angle of rotation, 0 to 2 pi. So whenever you are given a curve in one of the planes, so you can rotate it around the z-axis, you get some surface, and the parameterization of this surface is that one. Yeah, I have a better picture here. I'll show you. Here we had a curve in xz plane. So it was here xu, zu. This is this one. Because x is this, y is this, and then z is this. So we had this curve in the xz plane. And then we rotated it around the z-axis. And what we get is this surface of revolution, this body. And yeah, the parameterization of this body is given here. So xu times cosine v, xu times sine v, and zu. And u is from the initial interval, the same as this curve. And then v measures the angle of rotation. Okay, and the last thing which remains is to study the tangent planes to our surfaces. For example, if we compute tangent plane at this point, we get this plane. So tangent plane. And when we study tangent planes, it's natural to study coordinate curves to the given surface. So when we study tangent planes, it is natural to look at coordinate curves to our surface. And what are coordinate curves? So we have our surface FUV, and it has two coordinate curves. So first coordinate curves is we fix the first coordinate, fix u0, and we get some curve R dependent of V, R1 dependent of V, which is F U naught V. And again, we fix V naught, so the other coordinate, and we get a curve which depends on the first parameter. So it's F U V naught. So for every point, we have point on the surface U naught V naught, and every point lies on both coordinate curves. So this point from the surface lies on the first coordinate curve and on the second coordinate curve. And let's look on the picture of our surface of revolution, what would be the coordinate curves. So let's take P to be this orange point. And if we fix U naught, this means that the X coordinate is fixed. So X coordinate is fixed. Only the second coordinate changes. So the second coordinate varies. So we look what happens if we intersect. So this is X naught. This plane is X is X naught, and we intersect this plane with our surface, and what we get is a point. So this was not a good example. So let's take a point here. Let's take for the point. Let's take X1, Y1, and intersect it. So we fix the X coordinate and intersect our surface with the plane X is equal to X1. So this plane, the parameterization of this plane is X is equals to X1. And the coordinate curve is what is the intersection of this plane and our surface. In the intersection, we see that is something like that. So some curve like that. So this is the coordinate curve in the point X1, Y1 with the fixed X1. This is one coordinate curve, while the other coordinate curve in this point is when we fix the second coordinate and we intersect our surface with the plane Y is equal to Y1. And the intersection is then a circle. And this is the second coordinate curve. So in the point X1, Y1, we have two coordinate curves. The one where Y is fixed is the circle, by definition of the circle surface of revolution. And when the first coordinate is fixed, it's some curve, which is not a circle, but it's some curve. And what does this have to do with tangent planes? So in this point, we can compute both tangent vectors. Tangent vector to the orange curve, let's say this one. Oh. So this one. And also the tangent vector to the violet curve, to the other coordinate curve. So this is this one. So we have two tangent vectors. And tangent plane should be perpendicular to both of those vectors. So I mean, the normal of the tangent plane must be perpendicular to both of those vectors. So how to get the definition of the tangent plane, the normal to the tangent plane? We have to compute both of those tangent vectors and their cross product, and we get then the normal of the tangent plane. Maybe on other pictures it will be more clear. This is a a little bit difficult to imagine, but so what we computed, the tangent vector to R1V is so derivative with respect to V, and this is just the derivative of F with respect to V in the point U naught V naught, and then the tangent vector to the coordinate curve R2U is derivative with respect to U, which is the partial derivative with respect to U to the our parameterization of the surface in the point U naught V naught. And so the normal of the tangent plane is just their cross product. So we have the normal, and then the equation of the tangent plane is so we need tangent plane in the point U naught V naught. We already know the normal, so all the points will be U naught. So will be U naught V naught dot product with the normal. This will be UV dot product with the normal. So this is the equation of the tangent plane. U and V are parameters. Of course, here should be F of U naught and here F of UV. So, sorry, here should be. So N is now, this N is from R3, so X, Y, Z. So X, Y, Z are parameters. These are points. These are Cartesian coordinates of the points in the plane. And if we take the dot product of the point on the plane with the normal vector we've just computed, we should get the same as if we compute the dot product between the normal with the specific point in which we compute the tangent. So this point is exactly FU naught V naught. So this point is FU naught V naught. This is the origin, and then in the point FU naught V naught we computed the normal, and so this FU naught V naught should also lie on this tangent plane. And so the tangent plane is determined as what we did at the beginning of today's lecture. So we need one point, which is FU naught V naught times dot product with the normal. We get this D, which is AX plus BY plus CZ. So the Cartesian equation of the tangent plane is D is equal to AX plus BY plus CZ. The normal is ABC. And we get D so that we compute the dot product between this normal and specific point, which is FU naught V naught. And this is everything what we need to get the tangent plane.
So here X, Y, and Z are arbitrary points on this tangent plane.
Yes. X, Y, Z vary along the tangent plane. Yes, exactly.
And u0, v0 are points on our surface.
Yeah, this is specific point in which we computed the tangent plane. U0, so for example, we computed the tangent plane this point. So this point depends on, for example, u0 v0, and it's exactly f of u0 v0. This point is f of u0 v0.
But why then we need these coordinate curves?
Coordinate curves, they were so that we saw that how to obtain the normal. So we need two vectors from the tangent plane, and how to get those two vectors, we determine the coordinate curves, and from each of the coordinate curves we get one of those tangent vectors. They were only needed to see how to get two vectors from the tangent plane.
Okay, I understand. Thank you.
We could choose another two planes. So here we took coordinate curves. We could take any two planes which are not parallel. So any two planes which go through this point, and then got the curves. So the intersection of those two planes with our surface, and then compute tangent vectors. And it would work in the same way. But yeah, it's the most natural to take coordinate curves.
So if I understand you correctly, we can take two planes that are not perpendicular to each other.
Parallel. So they both have to go through the same point. So we are in this point. We would need two planes which go through this point, and they should not coincide. This means that they are not the same plane. This means that they are not parallel.
Yes. Okay, thank you.
And then we intersect the surface with those two planes, get two coordinate curves, not coordinate curves, get two curves, and compute the tangents to those curves, and everything would work in the same way. But it's also more natural to take those coordinate curves so that we can imagine what's our surface. So if you know both coordinate curves, we can imagine what our surface looks like. So let's look at the examples of coordinate curves for those examples we've studied today. So for example, the cylinder. So if we take a cylinder, you see, then and choose a point, for example, this point, what are the coordinate curves? So we intersect the cylinder with the plane with fixed V0. With fixed, so what we fixed here? Yeah, here we fixed V0. V0 is fixed. So the plane is in fact 0, 0 V0. No, 0, 0. X and Y are free. X, Y, V0. X, Y vary. So this is in fact Z is V0. And what is coordinate curve? Coordinate curve is just this circle. But now if you fix U0, so if you fix U0 here, then we are always on the same cosine U, sine U is the same. So we are on the same, let's say that this is in the XY plane. This is U0. So this point is fixed and V varies. So the curve is then cosine U0, sine U0, and then V varies. So we go up and down. So what we get, the coordinate curve is a line. And then the tangent plane in this point would be so the cross product of the tangent to the line, which is just the line, which is just the vector determining the line, and then this tangent here. So if we compute the cross product of those two, of this tangent line and of the direction of this line, we would get something which points out here. This is the normal, and it is in fact just the normal of the plane, of the tangent plane to the cylinder, of the plane touching the cylinder. So this plane would be this. It's really hard to draw everything in the same picture. Let's look at the sphere. Let's look also at the sphere. So what are coordinate curves for the sphere? We fix, so we have some point. It depends on u naught, v naught. So we fix u naught, which means that only v varies. So this v varies, which means that, so what is the coordinate curve? Cosine u, sine u, it's always the same. So u was this angle. So if we have xy, we have this point, we project it in the xy plane, let's say here, and this was u naught. And this is always the same. However, v varies, but this v measures this angle, this spherical angle. So this v goes from minus p over 2 to p over 2. And this point, in fact, travels here in the half circle, along the half circle. So the coordinate curve are 2 of v. This is f u naught v. This is half circle. And then we can do the same when we fix v naught and u varies. So here we are always with fixed v naught, and u varies, so this point travels along this circle. So this is r1v. This is f of u, r1u. This is fu and v naught. This is a circle. So coordinate curves are circles and half circles in one direction, because v only travels from minus p over 2 to p over 2. That's why in one direction we only get half circles. Okay, this is all regarding surfaces. We will do now 15-minute break, and then in the last 15 minutes, we will start with differential equations. Is there maybe any question regarding what we did this hour? Okay. In 15 minutes, so 11:43, we continue with a new chapter. So before we go to differential equations, let me just show you again how to compute the tangent plane. To see it from the other perspective, it then becomes more clear. Where is it? 47. Is this one? So you see we have this parameterization of our surface. We have a point R naught, and we would like to compute the tangent plane. So we need two vectors from the tangent plane, and we already have a point. So R naught is a point on the tangent plane. And we need two vectors. On the plane. So what we do, we calculated the tangent vectors to the coordinate curves. This is Fu and Fv. This is the partial derivative with respect to first coordinate, and then partial derivative with respect to the second coordinate. So this is E1 from the first hour. If you recall, when we parameterized plane, we had R naught was the vector on the tangent plane, and then we have A1 and A2, E1 and E2 as the direction vectors. And the plane in the parametric form is then just so R naught plus some scalar times E1 plus some other scalar times E2. So it's then the plane in the parametric form. What we did last hour was the plane in the implicit form, so in the Cartesian coordinates. So this is, in other words, we can write this equation as R times N is equal to R naught times N. This times means dot product. So this was N was ABC, and R naught is our point. So it's X naught, Y naught, Z naught, and this R is then X, Y, Z. Those are points on the plane. So this is what we did last hour. So these are implicit form and parametric form of the tangent plane. And sometimes you will also see the equation in this form with the Jacobian matrix. So this is nothing else but writing this parametric form in terms of matrices. So if we take for the first column, we take E1, so the tangent vector with respect to the first coordinate curve, and then a tangent vector with respect to the second coordinate curve as the second column of the Jacobian matrix. So this is by definition of the Jacobian matrix. And then Jacobian matrix times UV is nothing else but this U times E1 plus V times E2. This is only writing this parametric parametric form in a more compact way. So E1 and E2, we collect them in the matrix. This is exactly by definition Jacobian matrix, and then it's more in this tangent plane is written in a more compact way. So you will see all those three expressions meaning the same thing. So the idea is only we need two coordinate curves and their tangent vectors. And once we have a point and tangent vectors, we have everything. We have the tangent plane. And this is just the matter of the way of expressing this tangent plane. Okay, let's do now the introduction into dynamical models. So this is the last chapter. We will be dealing with this chapter for the rest of this course. So dynamical models. And we will study dynamical models through studying differential equations. Differential equations of different order and also systems of differential equations. First, we will recall what you already know. So what is the definition of differential equation? And some techniques how to solve these most easy forms of differential equations. So by now we had linear equations, nonlinear equations, so linear models and then nonlinear models. And what was the characteristic of the linear model? The characteristic of the linear model was that all the parameters in the model appear to the power 1 and no transcendental functions were allowed. Then in the nonlinear model, we allowed also transcendental functions of the parameters in our model, in our F, capital F. Capital F was our modeling function, if you recall. And now in dynamical models, except being nonlinear, we will also allow that derivatives of our unknown functions are present. So ordinary differential equation, this F is the ordinary differential equation. So differential equation, what does this differential equation refer to? This refers to that it contains, independent variables, independent variable, so independent variable here, it's not variables but variable. It contains dependent variable, and it also contains derivatives of the dependent variable with respect to the independent one. With respect to the independent one. So these are those x prime, x double prime, and then n derivative of x with respect to t. So in this form, t is the independent variable. It contains the independent variable t in this case, and then the dependent variable is x, and the derivatives are x prime, and then x second prime, and so on, x and derivative. And what does this ordinary refer to? This ordinary refers to that we only have one independent variable. So only the derivatives with respect to one, independent variable. So only one independent variable present. So if there would be, if there were two independent variables, then this differential equation could contain derivatives with respect to the first or the second independent variable. And in this case, we are talking about partial differential equations. So the difference between ordinary and partial differential equations is that ordinary contain only derivatives with respect to one variable, while partial differential equations contain derivatives with respect to different independent variables. So we'll study only ordinary differential equations. And this order of the differential equation refers to the highest derivative. So in this case, it's nth. So the highest derivative present. We only fix now some notation. And here, what's the difference between those two examples? Once we have this function where the independent variable is t and the dependent int x, while in the other form we have the independent variable x and the dependent one is y. Otherwise, everything is the same. Only that the variables, you will see different kinds of expressing the differential equation. So here we only switch t with x and x with y. Otherwise, everything is the same. Only the names are different. The names of the variables are different. It depends on the situation we are working, but otherwise the form of f is the same. Let's look at some examples. For example, x prime minus 3t squared is equal to 0. So what is f in this case? F is a function of t and x and x prime. It is ODE, ordinary differential equation of order 1, because only the first derivative of x with respect to the independent variable is present. And this function is x prime minus 3t squared is equal to 0. And you probably remember from last year or from a course you've studied. Otherwise, don't worry, we will repeat everything. So how to solve such an equation? So it's by the method of separation of variables. So here we will only solve it, and afterwards we will return to this method. So what we do is separate variables. X prime is 3t squared, and this x prime is in fact dx over dt is 3t squared. So dx is 3t squared dt. Recall that differentials can be multiplied, divided as if they were usual numbers. And what we do now is just integrate both sides. And on the left, we get x plus some parameter c. And on the right, we get t cubed plus some parameter, but I won't, plus some constant, but I won't write it because this constant can be put on the other side and joined with this c. So let's say that this c is a common constant. So this is the solution of our differential equation. So x of t, this is what does it mean to solve the differential equation? This means that we have to determine what's the dependent variable with respect to the independent one. So here the dependent variables was x, and yeah, we solved this equation. So x of t is t cubed minus c for some constant c. So we were able to solve this differential equation. to determine C, we need one additional condition. And usually it's called initial condition. So x at time 0 is x naught, some number. So we need to know what's the value of x when t is equal to 0. It's called initial condition. And once we have this initial condition, we can determine C. And now it follows that x of 0 is equal to 0 cubed minus C is equal to x naught. So from here we get that C is minus x naught. So from here we get that x of t is t cubed plus x naught. And this is called the particular solution of the differential equation. So this here is a general solution. And this here is particular solution. So geometrically, if we draw geometrically, what does it mean to have a general solution and a particular one? So the general solution is a family of curves, is a family of solutions, one parametric family of solutions. So xt equals to t cubed. This is this curve. So this is for c is equal to 0. Then if we take c is equal to 1, we have x of t is t cubed minus 1. We get this. So this is for c is 1. And then for c is minus 1, we have x cubed, x of t is t cubed plus 1. So it's here. So this for c equals to minus 1. So we are moving our solution x cubed up and down. And we get a whole bunch of solutions, one parametric family of solutions. But if we know one point on our solution, if you know one point, any point, so in our case, we knew that at x naught, the value at time t naught, the value was x naught. Let's say that the value was here x naught. Out of those solutions, this one is the one which satisfies our initial condition. So particular solution means that we pick exactly one solution out of our family of all possible solutions. And it turns out that if we have a differential equation of order n, then usually the family of solution is n parametric. So here we had, if we have here n, so differential equation of order n, then there will be n-dimensional set of solutions, and we will need n conditions to determine the true parameters. In our case, we had only the differential equation of order 1, so we had only one-dimensional family of solutions, so only one condition was needed to determine the particular solution. Okay, this was enough for the introduction. Next week, we continue with studying ordinary differential equations. Maybe some question for the end?
I have a question, but it's not related to differential equations.
Okay, then I will pause recording.